Alright, we made it to chapter 2. What we're going to do in chapter 2 to get started is we're going to review some basic mechanical energy concepts, and we're going to need these because these are going to show up later on in some of our equations. Alright, so we're going to review briefly about work, kinetic energy, and potential energy. Alright, so let's get started. Now what we're going to do to start out with, let's draw this little picture. Alright, so we got X, we got Y, like that. And let's have a path here. We've got a particle and it's moving along a path like that. Alright, so let's say it starts at this point O, and it's going to move along till it gets up to here. Alright, so it's got this distance. Let's call that distance S. Now at this point we could measure things, and we know it's going to have a velocity, which the velocity will be tangent to the path, like that. Now it's also going to have some forces. Okay, so this is on a curved path, so remember we're going to have a normal force. Now we'll also have a force that is tangent to the path, so we have Fs. Okay, now these two forces are components of the force F. So let's draw it like that, and let's make it look like this. So this force F should come all the way out to here, but I'm getting too much stuff going on here in this drawing. So there's force F. This is our resultant force. Okay, so hopefully you've seen that before in physics or dynamics. All right, and let's kind of write down what we just said was happening. So our body is moving from the initial S value, so let's call it S1. That's at this point O right here. And at that point it's got a velocity V1. All right. And for velocity, I'm going to write it as this capital V. So it's moving from that point to S equals S2 with a velocity V2. All right, so that's what's going on here. Now we've got these forces, we got Fs, Fn. We are mainly going to focus on Fs, because that is our tangential force. So if we go to Newton's second law, we know that that tangential force, which is Fs, has to equal the mass times acceleration. And acceleration can be written as dv dt. Okay, so this equation is going to relate that tangential force to the change in velocity. All right. Now if we use the chain rule from calculus, we know that Fs equals m dv dt. That's just repeating what we already wrote down. The chain rule then will allow us to say that that equals the mass times dv ds times ds dt. All right. Now if you look at this last thing we wrote, what is this? ds dt. If s is displacement, if you're taking the time rate of change of displacement, that's velocity. So that means we could write m times v, where v is velocity, times dv ds. Okay. Now that we've got that, let's look at this. So now we've got Fs equals this equation here. Alright, now if I move the ds over, we could integrate both sides. So let's write that next. And I'm going to flip the order here. I'm going to put mv on the left side just to follow along with what my notes have. Okay, so we're going to have the integral going from v1 to v2, where those are velocities, times mv dv. That's going to equal the integral S1 to S2 of Fs ds. Okay, And remember, these forces are vectors. Okay. So now we've got that. Now if you go through and integrate that, on this left side you're going to get mv squared over 2. You're going to evaluate at v1 and v2. And that one you could make equivalent to the dot product version of this integral over here on the right. So we would have the integral of s1, s2, fs dot ds. Let's make s a vector now. Okay. So let's go ahead and plug in these limits here on the left. That'll give us 1/2 m times v2 squared minus v1 squared, and then that's going to equal the integral on the right. Okay, and this is a dot here for dot product. So now what this gives us right here, this is our change in kinetic energy. So you've probably seen 1/2 mv squared. That's your kinetic energy term. Now this on the right hand side, this is work. So this is work of the force as the body moves along the path. And we're going to go from S1 to S2. All right, so this is a work term. Okay. Now remember, dot product gives you parallel components. Okay, so in order to have work, you've got to have a displacement that is in a parallel direction to the force. Okay, so keep that in mind. Work deals with, parallel displacements. Okay, so this is our work. So keep that in mind. We'll revisit that in a little bit. Next, let's go over potential energy. And this is something you should have also already seen. So here, let's draw a line. It's going to be a reference point. And now let's say we've got a mass here. So it's a ball. And this ball has some sort of weight. And then it's also got some resistance force, R. All right, so R is going to be the resultant of all other forces other than weight. So this would be wind resistance, everything else. All right, so think about throwing this ball up. All right, so here would be the second location. So if we look at the altitude, we could say the initial altitude is Z1, and then we want to measure from that same reference line up to the second location. Let's call that Z2. Okay, so just to write out what everything was. mg is weight. That capital R is your resultant force of all forces other than weight. Okay, now what we want to do is we want to find the work of each force. All right, so we got work of each force. And that's going to be found by 1/2 m v squared, this is v2 squared, minus v1 squared. And then that's going to equal the integral from z1 to z2 of r dz minus the integral from z1 z2 mg dz. Okay, so what we did here on the right hand side, if we look back up here, that's essentially what we did. All right, we have the dot product. So z is our vertical direction, so we're taking the r force, which is a vertical force, and we've got that with dz, and then same thing with weight. And then we're going to integrate and have our limits be at the initial and final elevations. Okay, and we subtract here just to get the correct sign. All right, so this is going to give you your equation that we need. And then if you look at each of those terms, what we have is, if we, let's see, let's reorganize this a little bit. Let's move this one to the left. So we'll have 1/2 m v2 squared minus v1 squared plus mgz2 minus z1, and then that's going to equal the integral from z1 z2 of r dz. All right, so now let's look at this. So this term right here, this first one, this is still kinetic energy. Now this one that we had from this right here, when we did work, this is going to be potential energy. All right, and then finally over here, we've got our work done by the external forces R. Okay, and the symbol for potential energy, usually we'll put delta PE. So delta PE is just going to be the weight times the change in the altitude. All right, so that's what we get here. So we just used our work equation that we had up here, developed it, and now we found that we have kinetic energy, potential energy, and the sum of those has to equal r times dz, or this integral. Okay. So now we've got that. Now our units of work for the SI system, we're going to have Newton meters, which is also joule, or you could say kilojoule. Right. In English, we're going to have foot-pound force, or BTU. Now our kinetic and potential energy, since they were in the same equation as work, those have to have the same units as work. All right. And then our conservation of energy. Remember, if the only force acting is due to gravity, then the sum of the kinetic and potential energies has to remain constant. Okay. So notice the key here is the only force acting is due to gravity. All right. So if you have external forces acting, that's not going to be the case, but that'll be the case if we only have gravity. All right, so let's stop there on this one, and then we'll pick it up in the next video. Thanks, guys.